Huge disclaimer. I feel like I really took the words like we're learning how to do this together and I ran with it. So I by no means think I am an expert in this. A lot of this is like relatively new material for me. So if I say something wrong, something that's not correct, or if you know of like a more efficient way to get these measures, just let me know. Because yeah, I'm really hoping this is more of like a discussion. This is definitely not me, like the all-knowing source conveying information. Okay, so we are just going to talk a little bit about odds ratio and relative risk. Let's see. Is that still working okay?
Yes.
Okay, perfect. All right, and again, this might be a refresher for some of you guys, but for me, these terms are always like fuzzy in my head. So just I thought it would be valuable just to think about what these two measures are. So odds ratio and risk ratio are some of our most common measures of association in epidemiology. You guys are all probably super familiar with them. And the odds ratio is just the probability of our outcome over the probability that our outcome doesn't occur. So for example, this would give us something like the ratio, or sorry, let me just move you guys so I can see my slides. This would give us like the disease odds given exposure status, things like that. So what are the odds you get a disease based on if you were exposed? And the odds ratio is super helpful to use when you don't have information on prevalence or incidence. So this means like you don't have full information on the entire population, who's getting the disease, who's not. This is when this is helpful to use. Okay. And risk ratio, risk, also known as incidence. I think for me, it's easier to think about it as the incidence. We get this basically from dividing the incidence of our outcome. So often in like epidemiology and probably what a lot of you guys are focusing on, this is like your outcome of death or disease status. And we can get measures like the risk in the exposed versus the unexposed. So this measures the probability of an outcome in the exposed group versus the probability of the outcome in the unexposed group. From the little article I read that was like based off like my presentations based off of, one of the biggest like takeaways I got from it is don't interpret risk ratios and odds ratios the same way. So the authors pointed out that a lot of times you'll even see in like published research journals the odds ratio being interpreted as the risk ratio with like probabilities. So just keep a lookout for that. Risk ratios, you're looking at like probabilities. Odds ratios, you're only looking at like you're looking at the odds of events happening. So that's like a word to the wise. And I can't go into the way complex math of how this works, and maybe someone wants to jump in and join. But odds ratios and risk ratios are like they will look different. So this is kind of going back to why we don't want to use them in the same way and interpret them the same way. So this dotted line right here is showing when the odds ratio equals the risk ratio. But as our risk increases or as our prevalence of a disease increases, the odds ratio starts growing way faster than our risk ratio. Um, and again, I think this is going on. Someone can jump in here. I think it's based on like the odds ratio isn't bounded. The risk ratio is bounded because it's like probabilities, but it's a little mathy. Now that we do have the rare disease assumption. So down here in the bottom left, when the risk is low, so that's normally like when our incidence is really low, or our prevalence of our outcome is really low, then the odds ratio and the risk ratio are actually pretty similar, and you can like interpret them in the same way. But like, again, word to the wise, just make it really clear to your reader what measure of association you are using. Okay. Again, I feel like this can get tricky when to think what ones to use. Summary from this article was suggesting using risk ratios, relative risk, anything like that when you have cohort studies or randomly controlled trials. So you have all the information on incidence in your population. So yeah, just anytime you can directly calculate the incident rate of your exposure, you can use risk ratios. Oftentimes, especially in case control studies, we don't have the ability to calculate the incident rate directly. So that's when the odds ratio is helpful. This is also really helpful for rare diseases because if you're trying to like get a cohort of people and see who gets the disease, maybe the disease is super rare that even if you pull in 10,000 people or 100,000 people, none of them are even going to get the disease. So then it's really hard to measure risk and through a cohort study. Whereas if you're just doing a case control study, you can find everyone who has the disease and then go from there. And again, odds ratio is helpful when you're just lacking information on incident rate and prevalence.
Natalie, can I jump in real quickly?
Yes.
So this slide. In Brazil, we have this famous epidemiologist called Facchini that worked with John a little bit, but he always said to me, easy way for you to know which studies you should use risk ratios and which ones you should use odds ratio. So risk ratios are those that you can observe. So if you can see that disease happening or that event happening, then you see a risk. But if you cannot see it, then it's odds ratio. Because when you see it, then it's probability. But if you don't see it, you're just guessing. So it's the odds. So like a cohort studies, you see the disease appearing and see the disease progressing or whatever. The same way for RCT. So you can directly measure it, so you can see it happening. Whereas for case control studies, people already have the disease, so you cannot see it progressing or appearing or anything like that. So you don't know how to use it properly. So you use odds because you're just guessing when did it happen or how did it happen. So when I'm trying to like remember when use a risk ratio or odds ratio, I see if I'm going to be able to observe it directly or not. Then I know if it's a risk ratio or an odds ratio. Just like, yeah, just a pointing out there.
No, that is super helpful. And I'm going to have to make sure to write that down when we're done. Okay. So
Yeah,
yeah,
Natalie, may I also just come in? Since we are talking about this, I really love the conversation. I just wanted to also add a few words. Yeah, I see here for risk ratio, since cohort studies, as Nathan said, it's easy to observe the disease being developed. So that also explains why we are not advised to use risk ratios for rare diseases. Because how long are we going to observe before this person develops this rare disease? So while for diseases that are easy to observe, to get a new occurrence, we can easily get a group of people who are all healthy or at a certain disease state or state of health. And then within short intervals, they develop the disease or whatever outcome of interest. Whereas for rare diseases, we don't want to wait a lifetime without seeing anyone develop the disease. So we just go into the population sample, and then since it becomes probabilistic, we use odds instead of risk because there is really no risk as per the definition of risk of developing the disease over a long period of time. Yeah, I just wanted to kind of corroborate what you guys are saying.
no, that is perfect. Thank you. And again, like I said, for me, this is tricky. Like it's tricky to keep the two separate. So like any input is super helpful. Thank you.
Yeah, let me say a little bit more
Oh
again.
yeah.
The odds ratio for rare disease is a good one because when we're talking about rare diseases, we usually cannot measure the prevalence of it because it's so rare. So one of the points of using odds ratio is because it overestimates. So when you compare, like you just show us the graph, the risk ratios and the odds ratios are always overestimated. It's always increased more than the prevalence itself. But when you have a rare disease, you cannot measure it properly because it's so rare. So you want to overestimate it to make sure that you know a little bit more of how the disease is happening in its dance itself. So it's important when you're talking about a rare disease, and of course there's some debate on whether the prevalence of rare disease should be considered. Like, is it 5%? Is it 1%? Is it 10% prevalence? Whatever, yada yada. But odds ratio is really helpful when you have this rare disease assumption because you can always project the numbers up to make sure that your odds are going to be like higher and you can guess a little bit more close to where a real prevalence will be for the disease, for the rare disease. Yeah, I just want to point that out before I forgot.
Again, yes, thank you. Okay. Now I thought it would be helpful to think about like how to get these measures in R. And again, this is where I'm thinking maybe this is helpful for some of you who maybe don't know or saw this a really long time ago. And some of you guys are probably like, I am a pro at this. So if you feel like you're a pro at this, that would be an awesome time to be like, hey, here's tips and tricks, or here's what I do instead. Full discretion, most of this is from like our biostatistics code. So I just like linked that, and Dr. Christine Markwalder, because I'm using the code from our code alongs in our data science class, in our biostatistics class. And again, if you guys are experts at this, would love any and all input. Okay, so when I think about the odds ratio, the biggest thing I think about is logistic regression. So the output from logistic regression is going to give you the log odds of your outcome variable, regressed on your explanatory variables. One of the biggest things that has already tripped me up is it's coming out as the log odds. So I'll show you, but whenever you're interpreting output from a logistic regression in R, you have to make sure you're exponentiating your coefficients in order to get like your odds and your odds ratios measured. If not, you're reporting the log odds. And then just again, quick word to the wise, make sure you're checking your assumptions about your data before you run a logistic model. I didn't think I'd really go into that right now, but make sure you're like, your assumptions are met. Okay. And I thought I would be terrible at coding in front of all of you guys. So I just did screenshots. But here, this is building a logistic regression model in R. So I've just named it a logistic regression. And what this model is looking at is the impact of mother's age, and that's categorized. So that's that MAGE-C variable on death of, it's like looking at the death of a child. So super happy. So what you can do is you can call this GLM function in R, and this actually has a bunch of our generalized linear models in it. You set up your formula for your model. So your outcome variable explained by your explanatory variables, your dependent variables. And then this is where you can adjust that GLM function to get different types of like regressions. So we're doing a logistic regression. So we have a binomial distribution, and our link function is logit. Again, I don't think I'm going to go way into like the nitty gritty of where all these things come from. And then you just specify your data. So Kenya F is my data. And one thing to note here is that death is a binary outcome. So we're measuring like a yes or no. Did this event occur? If we were measuring a continuous outcome, a linear regression would be better for that. Now, the nice thing is we can run our model. We can call summary on our model, and I'll show you what that looks like. But if we use the tidy function, then we can exponentiate our coefficients like I was talking about, and we can get confidence levels. So you can use the tidy function and the GLM function. Those are kind of like the two big hitters for logistic regression. Oops. Okay, there we go. So if you just call a summary on the model, this is what you're going to get. So you see that here is our like actual model that we built, and here are our coefficients. But again, remember, these are the log odds of our events happening, because this is just our general model. This is a summary of our model. And you can also see that we have things like our standard error and our p-values, but we're missing confidence intervals. So a lot of times you don't really care to report like the log odds without confidence intervals. So that's where that tidy function comes in. So we take our model and we can use the tidy function, and it's going to actually give us just like our exponentiated coefficients. So we have our intercept, and MAGE-C has 3 levels. So in this one, our reference group is MAGE-C 0, and then we have MAGE-C 1 and MAGE-C 2, because in MAGE-C we had 3 like different age categories for mother. So just to like practice interpreting this a little bit. So the odds of death, because again, we're not talking about probability here. This is like that warning sign. You can't say the probability of death. But the odds of death in MAGE-C 1 of our outcome variable, which is death, are 0.7571 times the odds of death in our referent group. So basically what this means is that MAGE-C 1 has lower odds of death than our intercept, which is our reference group, which is MAGE-C 0. And just for like helpful things, our age categories are lower than 18 to 49, and then, 39, that's a typo. And then 39 and above. And this kind of makes sense, right? This is what we would think. If you're a really young mother, your odds of like a poor outcome of death are higher. And then if you're an older mother, you would expect that. So we can see in MAGE-C 2, the odds of death in MAGE-C 2 compared to our referent group are 1.939 times higher. And then over here, it's really nice too, because in that far corner, you can see your confidence intervals for those odds. So oftentimes these are what you're going to also want to report in any statistical analysis. Okay. You can also calculate the odds ratio from a 2x2 table. I was trying to think of times when you would do this and not run a logistic regression, but I think it's maybe if you just have like a simple binary outcome, binary exposure. Someone can tell me if that sounds right. And you can use this package called Epi Tools. And this is kind of just like, I created a little data table, and this is what we got. So we have like a new tutoring program, an old tutoring program, and whether or not students passed or failed. So again, we're just like looking at odds ratios from a really simple 2x2 table. So in this case, we wouldn't really need to run like a logistic regression. We can calculate this directly. Ooh, okay. And it's really nice because data is all of my data that created this table. So you can just use the function odds ratio and put in your data, and it's going to give you your odds ratio. So how you interpret this is the odds ratio is 0.60456. So the odds that a student passes a test, so in this pass category, using the new program is 0.6045 times the odds of the student passing the test if they used the old program. So we can look at this and say, okay, our new program is actually less efficient than our old program. So we would want to keep using our old program. Again, I think this is probably less relevant to the type of work a lot of people are doing because it is just like a really simple 2x2, but just thought it would be helpful to show. Does anyone want to add anything about odds ratios? Because we're going to move on to risk ratios.
Yeah, I just want to point out that we have another package that is really useful for that, is the APR, EPIR, that is also really, really good on estimating odds ratio by in a table two versus two table, is how you say it. So you have like this, you can decide if it's a cross-section study, a cohort study, or the type of study that you're using, because it can add temporal information on it. It's really useful. And when you're using Fisher exact test, it gives you odds ratio straight from the test. So if you're just running a Fisher exact test, it doesn't need to be like in a package room or whatever. The basic R function works really well. It gives you the odds ratio because it's one of the main functions of Fisher exact test, to give you the odds of an event from a 2+2 table. So it's useful when you have like a rare disease that you're not using a logistic regression for some reason, and you want to describe the odds. Maybe because of like some bias or whatever, and you want to just describe your population, you can use the Fisher exact test to measure the significance and give the odds. It's really, really useful. But again, if you have the logistic regression, it's always useful to use it, even though sometimes for a cross-section study is not always the appropriate use of it. So yeah, that's it. Sorry.
Oh, that's so helpful. Thank you. Does anyone else have anything they want to add?
No, I just wanted to finish up, Natalie, on this example for the 2x2, which is pretty common to do the discussion between should we use the tests such as the Fisher's or the chi-square test, or do the odds ratio. And I guess this is the question: if do we want to see the magnitude of the association? Like the odds ratio would give us this idea of 0.6 or 1. In the example you are showing us 0.6, versus just testing to see if they are significantly different, or at least different from the random sample there. It's always a choice. And of course, you could do, if you do the logistic regression itself, you can also test for the significance of the odds ratio that you find. So many ways to do the similar answer, I guess.
Okay, perfect. Thank you. I know, which like my brain kind of hates. I just like want one foolproof formula that works
Yeah.
like that. But okay, and then risk ratio measures in R. So again, jump in at any time.
Sorry.
Oh yeah, go Edwin.
Yeah, sorry. I had a question on the odds ratio too. Maybe something we can think about. We understand that the odds ratio overestimate in non-rare outcomes, the outcomes which are not rare. So is there an alternative to use better measure of association for maybe cross-sectional studies, which are not, maybe they're not a cohort, they're just cross-section observational data?
I don't know. Does anyone want to
Just
add?
something to think about in the room, yeah.
Yeah,
Yeah,
I think there is, can I go?
Okay, I go, Bali.
Oh yeah. Yeah, I think in the cases where Edwin is describing, it may be preferable to use the prevalence ratio or the incidence ratio, depending on what one wants to achieve. Yeah, ideally, when one uses odds ratios where the prevalence is very high, they kind of overestimate. So in that case, either prevalence or incidence ratio, depending on the research question, may be more appropriate.
And is there like a cutoff for rarity? As in maybe 10% or is it 20%?
That one is hard to say. I'm not sure. I don't know.
The article I read was not helpful in this area. They said 10%, but then they said, but no one really agrees on that. So
Yeah, I'm gonna jump in. Sorry, João, you're gonna say, just go ahead. Yeah.
No, go ahead. I would just comment that this is really nice discussion.
Yeah. No, the prevalence ratio is a good alternative when you don't have like a rare disease. So if you have like a 50-50 or something more close to that in prevalence, when you have a binary outcome, you can try to adjust like a Poisson regression with robust variance, because when you have like this huge prevalence on a binary outcome, you can have overvariance of the data. So when you're doing regression, a logistic regression would probably not be a good idea, but you can use a Poisson regression and try to estimate it by the prevalence and do a prevalence ratio. But for you to be able to do that, your sample needs to be big. And I say that because if you have like zeros in a table that you're doing that, because you do like, you're measuring the prevalence of each variable that you're using. So, and that depends on like, if I'm using mother's age and then the number of appointments that she had in prenatal appointments, and I don't know, any disease that she had when she was pregnant. Are 3 variables, and then I need to combine those 3 in a single line in its prevalence. So it's a little bit more like a bigger sample for you to be able to do that. But it works a little bit better when talking about a more balanced prevalence disease. So you need a bigger sample because you have a bigger prevalence. So that's the thing. It's useful when you use like data from information systems that collected it routinely. I always struggle to say this word. Like you have in Brazil with the data source. So it's collected every single day and you have like lots and lots and tons of data. So that's really helpful. But sometimes you have like, you have to choose to aggregate some variables, you have to choose to aggregate some information to make sure that it's going to be useful, because again, it has a tendency to overestimate and overvariate. So the variance is going to be huge and it's going to be not a good model. So sometimes it's useful to have a Poisson with robust variance, but you need to be sure that it's going to be controlled enough to use it. That's it.
Yeah, I think maybe we could maybe future discuss more about alternatives to logistic regression, especially for cross-sectional data, which is really common in our practice. So yeah, to have more of this conversation, I think it's really nice.
Yes, I agree. This has already been so helpful for me. And this is perfect. This is what I was hoping this presentation would be like, where we're all just discussing. Okay, let's move on really quick just for sake of some time. And let's just talk about risk ratios. So 2 ways you can get risk ratios in R, and again, jump in with more, is log risk and linear risk models. So log risk and linear risk regression. And both of these you're using when you have binary outcome data. If you run a log risk model, you're going to get risk ratios as your output. And you do still need to exponentiate the coefficients. So anytime you see that log, I always think like exponentiate when I see a logistic or ln. One of the biggest things here though, is when I first learned about these, I was like, awesome. Why would I ever not use these? Because I like thinking in risk ratios way more than I like thinking in odds ratios. But oftentimes these models don't converge, which basically means like, I don't know if I understand the math super well, but basically the model's not going to be able to run given your data and confines on your data. Does anyone want to add like what causes that specifically? I just know I've gotten the scary output in R where it doesn't converge. So
Do you have an idea, João? Because I have no idea.
okay, sweet. Maybe that's a thought for future discussion. But you will know in R if your model does not converge. So you're never going to be like, did it work? Did it not? So I think like if it works, it's awesome. Oftentimes it's not going to work. So you're not going to be able to use it. So with that being said, I don't think we need to spend a ton of time talking about like how to run this, but our big difference here is we're just changing our link function. But we're still using that same GLM function to call a generalized linear model. And we can still use our tidy function, which is, I think, in the Broom package. Is that correct? Just to get like a nice output that's really pretty to read and interpret. Again, this is best case scenario if this works, at least for my brain, because if you can interpret this or if you can get it to run, it's really easy to interpret compared to like odds ratios. So for here, our intercept, which remember is our reference group, the risk in our reference group, which is MAGE 0, so those young mothers, it's just directly 0.145. So you can just read that directly, which is really nice. Our coefficients, so for MAGE C1 and MAGE C2, so these coefficients right here, those are the risk ratio of the outcome associated with a 1 unit change in our X variable. So basically moving up each H category, this is your risk ratio. So we can see the risk ratio of death in MAGE C1 is 0.784. So the risk of death is a little lower in that MAGE C1, that middle H category, compared to our referent group. Okay, linear risk regression is really similar. It estimates risk directly. So this is really helpful if you ever want to measure like risk difference, things like that, not a ratio. Same thing though, I think you have really similar problems with the model converging. It doesn't always converge. And one thing that trips me up with linear risk model is we can still have a binary outcome variable here. I think I hear linear and I'm like linear regression, continuous variable. But with this one, we are still allowed to have like a binary outcome. So we're just doing the exact same thing. We're calling our same GLM function. We have our same formula with death as our binary outcome. But this time we're changing our link function to the identity function. There is a nice way of just pulling all this data again. Tidy, we're getting really comfortable with this and we can see, and here is the output. Sorry, I just slammed this all on one slide. And this is just showing us risk difference. So if we come here, we can see the risk difference in MAGE C1 is 0.03 less than in our reference group. So again, way easier to interpret, not always going to converge. And I wanted to show you guys the link com function. And then I also wanted to ask your input on it and if anyone has found it more useful. Link com function will give you like a really similar output. So here's our risk in our intercept. Here's the risk in our MAGE C1. Here's the risk in our MAGE C2. So it's giving us similar output to our tidy output and just the model output. But in my mind, this is a trickier function to run for me. Like I always have typos because you're basically, like you're saying, okay, I want the intercept, I want the risk in the intercept, and then I want the risk in the intercept plus my first category, plus my second. So if you have like a more complex model, I think this could get really tricky trying to correctly add up all these terms to get the correct output. So I steer clear of this whenever I possibly can, because I also like miss a parentheses every single time. I don't know. Do you guys have any input on when this is like, are you like, oh, this is so valuable when we do it this way, or I steer clear of this one, or any tips on this function? Or do we just like not use that? And I would be fine if everyone was like, I never use Lincom.
Yeah, I used Lincom a lot as a student, but I'm happy to learn about the tidy because sincerely, the tidy function looks a little much in quotes sexier than the Lincom function. So I would go for the tidy. It's just simple. Yeah.
I agree. I think it's way easier. And I think it's a little more intuitive to think through like the arguments that you need to add for the tidy function. Does anyone else want to add?
Yeah, I don't usually use Lincoln function. In fact, it's the first time that I'm seeing it.
Okay. Honestly, this is comforting. I was hoping it wasn't like so well used because I hate it. So this is good. Okay, yeah, but I just wanted to make you guys aware. Oh, sorry.
Yeah, I think the Lincoln function is the same that we use even in Stata. It is sent for linear combination. So that's why you see it is adding the intercept value, the coefficient of mother's age, same coefficient, the mother's age, and the second coefficient, instead of adding them manually. It's helping you adding it.
Okay, interesting. And then it's similar or same in Stata. And I have like literally zero
Yeah.
experience with Stata.
We use them more we use more when we have interactions. We are testing for interactions. Yeah. Yeah, maybe Edwin and William, they can add more on this.
Cool. Yeah, that would be super awesome because this is like a big messy gray area in my brain. Okay, that is all I really had prepared, and I think I took up a lot of time. But if anyone wants to like add, if we want to have more questions, I don't know, Natan, do you want to take it over from here?
Yeah, let's see if people can want to add something, comments. I just want to thank you in advance and say great presentation. That was really, really nice. Does anyone want to add anything to the topic? Want to comment? Want to share experiences?
Well, I would just want to thank Natalie Matthews for the great presentation and also for bringing up this topic. I think that is the very essence of having such sessions. Sometimes we learn something new, sometimes it comes like more of a refresher. So, I mean, that's what the world is about today, learning, unlearning, and relearning. Yeah, thank you very much for bringing this up.
Anyone else wants to point out?
Oh,
Yeah,
go ahead, Edwin. Sorry.
yeah, I want to thank Natalie also for this nice discussion. And also I wanted us to think about another thing. Natalie spoke about how to interpret differently the risk and the odds. So is there like a main difference you should always keep in mind while interpreting odds ratios and risk ratios?
Sorry, Edwin, it was a little hard to hear you. Do you mind repeating your question?
Yeah, there's something to think about, as in Natalie talked about the difference in interpretation and how some papers misinterpret odds and risk ratios. Is there like a difference you have to keep in mind when you're interpreting odds ratio versus risk ratios or the other way around? Is there like a key point that you should always remember while you're interpreting them? That's what I wanted us to think about.
Yeah, I guess it comes back with what Natalie was showing through the rule of thumb of what they both mean. So the risk ratio would be more close to the reality, right? Because you're having a randomized study, you are having a cohort study, you know, a prospective study that you are, you know, seeing the population, seeing how the disease progresses, you know, actually measuring what is really happening to that population. While for the odds ratio, it's most likely you're going to use on a retrospective study. You know, you had a case control study or a cross-sectional study from your patients, and you are estimating this odds between having the outcome for one group and having the outcome for the other group, or the other way around. So I guess how reliable they are and how even how you write your result is something that you need to be careful of, because you cannot say that if you cannot say that the odds ratio is like they are more likely to have the condition, they have a higher risk. You need to be really careful on how to frame that. And usually saying directly odds, they have a higher odds, it's better to not misjudge or mislead the person that is reading your publication or your results to understand, so they think that your results mean a different thing. I guess that's how the rule of thumb there. The risk ratios are more reliable, more close to the actual truth, but they are more difficult for you to estimate because you need a different study design, which is often more, you know, you need a cohort or a randomized trial, which is not feasible in many conditions.
Yeah, makes sense.
Yeah. Natalie, I would also thank you for your presentation. It was great. Really, really good way that you presented the concepts. I love that the paper was like this tutorial vibe, this discussion really, you know, narrows down to the topic. And it's one thing that we use very often. We are always modeling, we are always doing logistic regression, and it's really good to have that refreshment and this discussion. And maybe one question that I would have for you is which one would you use for your thesis? And if you could tell us something that you want to estimate with your thesis, for instance, just so we can think about how this is applied.
Yeah, I can think out loud. So I might be like a little jumbled. So for my thesis, for those of you guys who don't know, I'm looking at cesarean rates across different like municipalities in Brazil, and cesarean outcomes. So I think as I think out loud, like we could think about one outcome. Oh man, they maybe have a class in the room I'm in. Okay, I will finish super fast and then they have a class in here. Yeah, so I could imagine potentially wanting to like estimate the risk of having a C-section in different wealth levels of different municipalities in Brazil. So for part of my thesis, we're going to look at like kind of the WHO categories of wealth, and like apply that framework to municipalities in Brazil. So like low income, middle income, upper income. So I'd be curious to measure like, okay, what's the risk of having a C-section in these different income levels? And I think that would be a binary. And this is where I get a little tricky because I have all this data from 1996 to 2021. So in my mind, I'm like, I could observe it when Natan was saying that. So I think I would be okay to do the risk. I don't know. Does that sound okay?
Yeah, I think so, because the way that those that data collection works is that every single birth is reported. So you can have a pretty good measure of this, like even though it's like an ecological measure, you have you know, this high level view, you don't have specific, you know, patient identifications, or you're not following these patients. It's supposed to be every single patient in the country, every single birth should be reported. So I guess you would do fine with the risk in that situation. But it's
Yeah,
something to think about, yeah.
I think it's fine because her outcome is not like birth, it's not birth related, like it's not about the newborn, is about the C-section. So you're observing the C-section, so that's your object of observation. So you're measuring all of this. So if you have this data, then it's fine. I think it's fine for you to use the risk because you're observing all the C-sections and how it like went, if it went well, if it's related to wealth, if it's related to the number of appointments in the prenatal or whatever. So I think it's fine to use the risk because you're not like expecting anything else from that. You're just like observing it, measuring how many times it was made, like how many sections we had and stuff. So I think that the risk makes sense to use in that situation. If it was something like an outcome for the newborn because of a C-section, then it's probably not the best one to use the risk because we don't have this information really well. But since you're looking at the C-section numbers, you have this because every C-section is counted in Brazil. Like probably not everyone, but the most we can get because this is again, probably the best system that we have along with the mortality one. So those two are the best ones, the birth registry and the mortality registry. So I think that it's okay for you to use the risk because you're preserving the number of C-sections and any outcome from it, just with C-section itself. So I think it's fine to use the risk and not the odds.
Right. Nice.
Yeah, may I also add something, and especially with respect to design, because when we are using data that has been collected, there is a little caveat that if we are not careful, may really hold us back when it comes to, because one of the first questions would be, is it going to be kind of, in this sense, prospective or retrospective? But whatever the case, it will be important to define inclusion criteria a priori. So kind of try to blind yourself on the outcome of interest and say that, okay, I want patients who have met this condition, and then select them using some random process, and then now follow them through, look at the data to see those who develop the outcome. In that case, you'll be basically mimicking a true cohort study, although you are dealing with kind of available data. If not,
Yeah.
the pitfall could be that you would select a particular group of individuals, which is kind of biased because it meets some conditions. And then because of that biased data set, you erroneously also have biased results. So look more at how you enroll the participants because that will make the difference. If not, it could be more of a cross-sectional study, but you can make it cohort depending on how you enroll your participants. Yeah.
Super
Good.
helpful. Thank you.
Well, just for the sake of time, and Natalie needs to leave the room. Let's wrap up here, I guess. Thank you everyone for coming. Thank you, Natalie, for your presentation. It was really fun and interesting. And thank you, Nathan, for hosting that.
Yeah, thank you so much, Natalie. You're free to go.
Thank
I just wanted
you.
to point out
Thank you.
again that we still have some